Hey everyone, welcome to our virtual lab. And in this little short tutorial, I want to just give kind of an informal discussion about the Wiener process and also how it's related to the so-called Gaussian white noise process. So what is a Gaussian white noise process? So Gaussian, right, which is really the same thing as normally distributed. So a Gaussian, we also say it's white noise, and I'll tell you why in a second, process. So it's a stochastic process, it's a random function, is denoted, say, like epsilon of t, where each t, epsilon of t is normally distributed, say, with 0, sigma. So it's kind of a mathematical fiction, saying that, hey, at every time, and we know time is continuous, so at every little piece of time, you've got this normally distributed random variable. So you can imagine, what this thing looks like. If you think of like a normal, say, Gaussian sequence, which would be at fixed points in time, right? You'd have a normally distributed random variable. So what might that look like? And let's say we have something like that, maybe you get 3 sigma number here, you get another one, you get something like that, right? You'd have discrete sets of points at each time, and each one would be a normally distributed random variable with 0 mean and say variance sigma squared. Now imagine you let these things get really close together, right? You wouldn't be able to even draw it. It would just be this wild, jagged kind of thing. And that's this white noise process, right? It means every instant of time we have a normally distributed random variable. So once again, if we think of it as the limit as you take these time steps going to 0, and without getting into all the mathematical gore, effectively it's really a mathematical fiction, right? But it's a useful mathematical fiction because we're able to use continuous time and all the great properties of stochastic calculus to get some great results, which we then can discretize. In other words, we know the world is discrete in nature, but we pretend it's continuous, and that allows us to develop some great formulas and theorems and things like that. And in the end, we have to go back to the discrete world anyway, right? So we're going to discretize whatever solutions and things we get anyway, whether it's a solution to, say, a stochastic differential equation or something like that. And that's the whole Black-Scholes formula is built on the idea that we're in continuous time, even though we're reality, things are not continuous in nature. So just remember, remember the Wiener process. Right, the Wiener process was defined implicitly by a couple of statements. So we'll call this thing, I'm going to use z of t here, okay? I know we use x of t in our lecture notes, but I'm going to use z of t. And the four things are, number one, if we think of z of t, and we usually say t is greater than or equal to 0, has stationary. I'm not really going to get into what stationary means. Just means the distributional statistics remain constant over time. So we're going to not get into that really. But it has independent increments. And what do I mean by independent increments? I mean that if you think of z of t1 and z of t2, and you take the difference of those two, that's independent of z of t3 minus z of t2. So what happens between time t1 and t2 is independent of what happens between, say, time t2 and t3. And in general, that's true for all finite intervals, non-overlapping intervals. Okay. So once again, this is kind of a loose discussion here. Two, probably most important, is that z of t is normal. So in other words, for any particular t, z of t is normally distributed, right? Three, it has zero mean. And then four, it's just the probability that z of 0 is equal to 0 is equal to 1. Okay, so it has zero mean, right? So this thing has a zero mean, it's normally distributed, and it starts off at 0 basically, right? So we might have, for example, something that looks like this. Right? That would be one, say, sample realization of the process. And it can be shown, right? It can be shown that z t minus z of tau is normally distributed 0, sigma times square root of t minus tau. So the variance, right? The variance, right? So the variance, and we wrote this as, right, delta, say, z is equal to epsilon times the square root of the change in time, where epsilon is normally distributed 0, sigma. So, right, we wrote it like that. The change in z is just equal to a normal random variable times the square root of the change in time. And so the variance grew with time. And I know I showed you those graphs where the reason why we have this sort of square root of t is so that the variance per unit time, when we let time decrease to delta t decrease to 0, that the variance of the process per unit time remains the same. It doesn't go to 0 and it doesn't go to infinity, right? It reaches a constant. Right, it reaches a constant. So we write sort of this thing. Well, I won't get into that yet. So, so basically, it's it's a process that's at each time, it's a normal distributed random variable, but the variance of this thing, right, is growing over time. As opposed to this Gaussian process over here, where the variance is the same. And every time, the variance is just sigma. Over here, the variance is going to be, variance will be sigma squared, sorry. And over here, the variance is going to be sigma squared times, right, times time. So it's kind of a random walk, right? It's a random walk with normally distributed steps. Now, just kind of quickly, remember from our stochastic light discussion about stochastic calculus, I just want to kind of point out a couple things. Just like in regular calculus, there's sort of this hierarchy, right? You have stochastic processes that are mean square differentiable. You have stochastic processes that are mean square continuous. Remember, that means the expected value of the process squared, right, as approaches some value is equal to the value of the process, right? So everything is in terms of mean square here. And then on top of that, sort of overarching is this whole thing about is mean square Riemann integrable, right? Riemann integrable. So in other words, a random function could be integrable in some sense. So mean square differentiability implies continuity, but not vice versa, right? You can have functions that are mean square continuous, stochastic processes that are mean square continuous, that are not differentiable, just like in regular calculus, right? You can have continuous functions that are not differentiable. And you can also have, integrable functions, which are not necessarily continuous, right, in a Riemann sense, right? So that's kind of the hierarchy. All right. So so what we can do is we can show that this Wiener process, right, this Wiener process z of t, which we don't really have a formula for it, we just have this implicit definition. This Wiener process we can show is mean square continuous, and therefore it's mean square Riemann integrable. I can add it up in some sense, but it's not mean square differentiable anywhere, right? And so it's this, it's this kind of very jagged, kind of random walk, very jagged, random walk. If you think back to calculus, think of a function like function that's f of x is equal to 0 if x is rational and equal to 1 if x is irrational, right? It's got these infinite little jumps, it's got these jumps, right? Everywhere. And so kind of the same idea, you get these jagged jumps everywhere, right? Even though it's mean square continuous. So even though we write dz is equal to epsilon t times the square root of dt. We write this in sort of differential form, we write that in differential form. What it really is, I mean, that statement doesn't, what does it mean? It doesn't really mean anything. It really means, because we already said it's not differentiable, right? This guy over here, right, would be my Gaussian white noise process. Every time t is just a random variable. There is no such thing as dz dt in any mean square kind of sense, but we write this in a formal way, and what we mean by that is that, we really mean by that is that z of t is equal in a sort of mean square way, right? It's equal to this definition from integral from 0 to t of this Gaussian white noise process. Okay, so Gaussian white noise process. So, and so we can show, right, this can be shown. Of course, this integral we've never seen before. It's what's called an Ito integral. We're not going to really delve into that. Once again, we're flying at a high altitude here. But suffice it to say, it can be shown under certain definition that this is true. So in a sense, we can think of that dz, even though we know this derivative doesn't exist, we kind of think of it formally as equal to this, right? And in some limiting sense, we can show that to be true. That the derivative of this thing, remember this thing is just a random walk, which means I'm adding, right? I keep adding these normal random variables to it. And so if I take the difference between two, right, it should just be equal to the Gaussian process, right? And so that's kind of formally, what we're saying. It's kind of really not true. It's meant to be understood in sort of an integral form. So that just quickly, I just want to kind of quickly just remember this brings us to our, and I'm going to post on the video showing you those charts again that we showed in class, and then also just showing you how if you take the difference between two time steps and you look at that, you get that Gaussian process. Okay, so be on the lookout for that video also. So we have the general Brownian motion, if I will, I guess I'll call it general Brownian motion, which we're going to use. So general Brownian motion was dx of t is equal to mu dt plus sigma dz dt. Okay, so this dz of t, so if we wanted to, you can think of this as a differential equation. It's a very kind of formal statement. dt is equal to mu plus sigma dz dt over t. Remember, this guy over here would just be, in our formal sense, it's just equal to that Gaussian process, that process that at every time t, it's just a normal random variable. It's like a normal disturbance. And once again, this is just more of a formal statement, right? Because this is not really differentiable in any sense, and really it's a formal statement for the fact that x of t minus say x of tau is equal to the integral mu dt plus somehow this other integral of sigma dz. So this is the true mathematical statement, and this once again gets into what we call the Ito's integral. We need to somehow figure out how do we integrate something that has this random differential, right? It's not dx, it's just this random thing. And so that involves something that's a little bit above our pay grade. We're not really going to go there, but this is just to give you an idea of, of how this the Wiener process is related to this, and the general Brownian motion is related to this Gaussian sort of function, right? Gaussian random process. All right, so kind of just gives us a kind of review. This is the formal equation, if you will, that is used to define this general Brownian motion, right? And then we usually just write this as kind of a shorthand way of saying this. So anyway, that's it, and be on the lookout for that other video I'll post, just showing you those charts again and showing the Gaussian process, and then I'll probably post one more video up, just going through an example of the simple form of Ito's lemma, and then when we start class on next week, on the 30th, we'll talk more about looking at this Brownian motion as a limit of a binomial model. All right? All right, so thanks for coming, and we'll see y'all soon.